So for today, there's not going to be any slides. It's basically going to be me going or us going through FLAC2D project. We're going to start from scratch. All I'm giving you here are these two files, two grid files. And the consensus was we're going to look something at like a tailings dam. We're going to look a little bit about fluid flow in the tailings dam, and then we're also going to look at taking a pore pressure distribution and applying it, interpolating it into another grid. So that's why I have two grids here. The first grid, grid 1, tailings dam grid 1, we're going to do a little fluid flow analysis, and that generates just pore pressure distribution. And then we're going to take those pore pressures and we're going to interpolate them onto tailings dam grid number 2. Not really like a typical workflow, because we kind of have to make a pore pressure distribution and then interpolate it. You'll probably have your pore pressure distribution from piezometers or some other data. So, but I didn't come up with any of that. So we're actually going to make one using FLAC2D. Okay, so that's kind of the idea. And we're gonna get a little bit of everything, I think. We're gonna do fluid flow. It's gonna be uncoupled. So it's not gonna be the whole rigorous coupled mechanical, hydromechanical analysis. I figured that was just a little too overkill, and we're kind of focusing more on Python in this section. We're gonna look a little bit about writing lists of data to a text file using splitting, which I think is actually a pretty useful thing to do instead of just looping. And then we're going to look at the Python file itself using a SciPy package called, I think it's called interpolate, to do the actual interpolation. All right, so basically what we're going to do now is we are going to do a flow analysis uncoupled, so as simple as you can possibly make it. So I'm wondering if I should just say go do it, and it'll test you at the end. No, that'd be awful. So this is what I'm going to do. I'm going to hide the answer, and we'll go through a little bit at a time. All right, so we're going to start by making, you can open a data file. I call mine generate pore pressure. And then the first two lines I'm sure you guys are familiar with. We create the new model. We just clear out the model state on the first line. We set the large strain mode to off. And then the third line might be a little different. This is actually how you import those grid files into the program. So that is Tailings Dam Grid 1. Remember, FLAC doesn't care about case sensitivity, just as long as you get the name right. So go ahead and we'll just run these 3 lines and then look at the grid. All right, and then we can go to the model pane and just take a look at this. Very simple, like I said, as simple as you can make it. I just gave 2 group names when I was making this in Sketch. In the construction slot, you can see here, this is the base, and this is the dam. All right, so I'm going to go back to my data file. I called it generate pore pressure. And this model was largely built on top of one in the documentation called bring it up. I'll bring it up later until we're all done. Basically, it's built off of one about dams in the documentation. And in that model, it's a dynamic model where they give a earthquake excitation at the base of the dam to see how it reacts to dynamic motion. So pretty well in here. I think we've all seen that before. Basically, we're just assigning a more Coulomb constitutive model to the dam, hence why pretty much everything has the range group dam. Notice I use the 3 ellipses a lot. I think it just kind of makes your code look nicer. You can just write it in one line if you wish. And then similarly, I do the same for the base, which we're just going to keep elastic. So when I initially made this this model, I was just using zone face skin. Remember that command will find all the surfaces in your model and assign them a group name. And it's basically based on a break angle, which is, if you just kind of look right here, we have basically a face here, we have to face here. And if this angle here was extremely shallow, so maybe this face went like that, it would just assign all those faces the same group name, same group. Be like, oh, this is just one face, so I'm just going to give it the same group name. But we want to distinguish this bottom from the tailings dam. So you basically give this break angle, and it says if it's at some low value, 25 in my case, then separate those groups. Yeah, I can't remember exactly how. I don't want to say something wrong. I might, in fact, let's just go to the. Yeah, okay. Specify the angle that is used to determine face continuity or congruity for inclusion in the skin group. The default break angle is 45. That's what I actually think what it was doing. Okay, so that's basically just creating those face groups so I can use them in the next line to apply my boundary conditions. East-west will be the two sides and then the bottom. And then for simplicity, we're going to turn gravity to 10. And then this next line, we're going to solve. And I added a little bit of extra keywords here. Elastic solving. So basically it just, in the entire model, it'll turn your strength values very high, so the model remains elastic. If I did not put an only, it'll change those strength values to be very high, so the model runs elastic. And then once it converges, it'll switch your strength values back to what you had given, and then continue to solve until it converges. It's basically a way to produce less impact on the model, so you don't make it all fail right away. And I'm using elastic only, meaning it only runs elastically, only uses high strength values while solving this time, because we're just allowing the whole thing to settle under gravity. I don't, we're in our model, we say the dam is there under the gravitational loads. Nothing has failed, so let's just keep it elastic. Okay, and I'll just run all that. So we can take a look at our model. Yeah, go ahead and make a plot if you haven't done so already. And I'm just going to show the stresses. Yours might look something like this. It's just a contouring method. Here you can change it from constant volumetric averaging or inverse distance weighting. All those methods are described in the documentation. It's just smoothing out the whatever you're trying to contour. And it's the vertical stress because we're in 2D realm where Y is vertical. And you can actually get the out of plane stress, which would be ZZ. And horizontal stress.